Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on antenna. Okay, so for this video, I'm going to continue the series of discussion on the key antenna parameters. This video, okay, I'm going to show you an example. How can we actually calculate the antenna temperature? Okay, so this antenna temperature is also known as antenna noise temperature. Okay, this is because noise is actually proportional to temperature. So when temperature increase, the noise also will increase. So hence, in order to understand better for noise on antenna, okay, we need to take a close look on the antenna temperature. This will be the part 13 series discussion on antenna. So guys, if you're keen to know more about antenna, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on antenna. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Okay, before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Okay, so these are all the key parameters of antenna. We have discussed all these parameters of antenna. Okay, so this video, as I emphasize, we will be going through the antenna temperature. Okay, what is actually an antenna temperature? Okay, so antenna temperature is a measure of the noise that is generated by an antenna in a given environment. Okay, which means that different environment you may have different temperature. So in short, this antenna temperature is simply to measure how much noise will be generated. Okay, so this is also referred as antenna noise temperature. This is not the physical temperature of the antenna itself. Okay, rather it depends on the antenna gain, radiation pattern, and also the noise they pick up from the surrounding environment. So basically, this is a quick definition of antenna temperature. To define the environment, and therefore we can actually provide a complete definition of the antenna temperature, okay, we will introduce a temperature distribution, okay, which represent the temperature in every direction away from the antenna in a sphere coordination. Okay, for example, the temperature of the night sky, okay, which is approximate 4 Kelvin. Okay, we need to be very careful about this. So this is something different, okay, what we are actually very familiar. Normally, when we actually talk about temperature, we associate with degrees Celsius, okay, but over here, keep this in mind, we will keep this temperature in the SI unit of Kelvin. Okay, so at the night sky, okay, the temperature is about 4 Kelvin, okay, while the temperature in the direction of the Earth's surface correspond to the physical temperature of the ground. So in short, when it's actually nighttime, okay, the temperature, we can take it as around 4 Kelvin. While in the day, okay, so basically we can take reference to the physical temperature of the ground, which means that let's say how much will be the temperature of the ground, okay, we take this as a calculation for the antenna temperature. The antenna temperature can be represented by the following formulas. Okay, so basically this is the formulas, okay, so-called to calculate the antenna temperature. Okay, so this equation shows that the antenna temperature is actually calculated by integrate over the entire sphere, okay, which means that the radiation pattern, as you can see from here, the whole of the antenna, let's say this is the ohmic direction, the whole of the antenna entire sphere, okay, based on the radiation pattern. So if let's say it's directional, hence this will be different. So basically, in short, it depends also on the radiation pattern of the antenna and also the temperature distribution of the antenna. Okay, so as mentioned here, so this R is actually referred to the radiation pattern of the antenna. Okay, so T is actually the temperature distribution of the antenna based on its surrounding. Okay, so basically this is what I have mentioned just now. So basically nighttime, we simply declare this as 4 Kelvin. As for the daytime, okay, it depends on the temperature. Okay, let's say we take reference to the temperature of the ground. This state that the temperature surrounding the antenna is actually integrate over the entire sphere and weight by the antenna radiation pattern. Okay, thus, okay, so as I mentioned, for isotropic antenna, okay, they will have a noise temperature that represent the average of all temperatures around it. Okay, because for isotropic antenna, we actually radiate, okay, so-called all over 360 degrees. So therefore, okay, we actually need to take the average of all temperature around it. However, for a directive antenna, okay, for example, we have a pencil beam, okay, the antenna temperature will depend only on the temperature in the direction it is pointing. Okay, so therefore, when we actually have a directive antenna, so basically it depends on which direction the antenna is actually pointing at. Okay, so coincidentally, an antenna temperature will vary depend on whether is it directional or actually aim into space or actually direct towards the sun. So basically, this is why the antenna temperature also depend on the environment, as you can see from here. Beside, okay, from the radiation pattern, okay, so basically it also depend on the environment. Okay, here's how antenna measurement actually work and how we can easily calculate it. So as I mentioned earlier on, okay, measurement for antenna temperature, we use this Kelvin instead of degrees Celsius. Okay, so the antenna temperature is usually measured in Kelvin. For this case here, where a higher temperature indicate more power from the radiation field being received. Okay, as for power relationship, okay, the antenna temperature, okay, so basically this is the antenna temperature, which is denoted by TA. This is actually proportional to the power density received by the antenna. Okay, the total received power actually can be easily calculated by shown over this equation here. So K is actually a Boltzmann constant. TA is actually the antenna temperature. Okay, keep this in mind, they must be in Kelvin. This B is actually the bandwidth. Okay, the receiver has a temperature TR. Okay, so basically this TR is actually belongs to the receiver. And hence for the total system temperature is simply, okay, the antenna temperature plus the receiver temperature. Okay, a parameters often encountered in antenna specification sheet for operation in certain environment is actually the ratio of the antenna gain to the antenna temperature. Okay, so basically in short here, these parameters most of the time we just denote G over T, gain over temperature. Okay, so this is what you mentioned here. So the antennas data sheet, okay, normally they will operate in certain environment. Okay, so therefore the ratio of the antenna gain, okay, basically to the antenna temperature. So basically we can use either G over T or we can use this dB versus the Kelvin. Okay, so T is temperature, this is gain. So when we actually express gain in dB and when we actually express the temperature as Kelvin. Additionally, okay, many RF engineer actually use the noise figure, okay, or noise factor. Okay, so basically, most of the time we actually know this as noise figure, okay, to describe a system performance. Okay, noise figure is actually the ratio of the input SNR to the output SNR. So basically, this actually measure the internal noise that is actually generated. So in short, this noise figure is actually the input SNR over the output SNR. Essentially all RF device, okay, whether is it mixer, amplifier, etc., all the RF device actually introduce some we call the internal noise. However, antenna temperature is not directly related to noise figure, as the power level of the signal input can vary significantly depending on the desired signal direction of arrival, while the noise contribute remain constant. Okay, so basically this is a quick, let's go through one more slides here. Okay, so a quick example. Okay, suppose you have the following values. Okay, we have the noise that we sorry, the power that we actually receive by the antenna, which is 2 nanowatts. Okay, the bandwidth of our system is 100 megahertz. Earlier on, I mentioned this. So let's say we want to calculate the antenna temperature. So we just move the K and B on the other side. So basically from here, you can easily punch your calculator. Okay, so hopefully I didn't make any careless mistake. So basically this is actually the temperature of the antenna. Okay, so next, another example, okay, for example, now we are tasked to calculate the antenna temperature in a system. Okay, so we are given parameters here. Okay, so the sky temperature is about 15 Kelvin. Okay, so this is to make it easy. The noise ground temperature, okay, which means that the the temperature of the ground, okay, let's say it's 290. Okay, so basically this can be referenced, okay, when we actually measure the temperature of the ground or any nearby object. Okay, the antenna efficiency, okay, is actually 0.8. Okay, antenna beam coverage is 0.6. Okay, so fractional of the sky that the antenna is. So basically, you just imagine, okay, so basically the coverage is not 1, but simply is less than 1, okay, will be at 0.6. So the formula to calculate will be by this equation. Okay, before I come to the discussion how we actually do this, let me break this into two parts here. So this is actually from the sky, and this is actually from the ground. Okay, so basically you can see over here the coverage 0.6, okay, is to the sky, and therefore I can assume that 0.4 is to the ground, as you can see from this equation here. Okay, so now we are ready to calculate. So let's do a quick calculation on the sky contribution first. Okay, the fraction of the antenna beam that is actually from the sky is actually mentioned here, okay, which is 0.6. So the effective temperature from the sky will be from here. So as I mentioned earlier on, we can break them into two. So let's quickly calculate for the sky first. So this is 0.6. Okay, the temperature for the sky, as it mentioned here, is about 15 Kelvin. Okay, so therefore from here, we can calculate that the sky contribution is 9 Kelvin. Next, okay, we need to calculate the ground. Okay, so as I mentioned, you can simply just take 0.4 multiplied by the ground temperature. So this actually gives us 116K. Okay, so we actually need to combine both of them, the ground and also the sky. So we simply just add them together. But keep this in mind, okay, we need to take care of the antenna efficiency over here. So therefore, this is the antenna efficiency. These are the two factors that actually add up. And therefore, you can calculate the antenna temperature as 100 Kelvin. Okay, so antenna gain pattern, okay, for more precise calculation, okay, you probably need to discuss about the antenna specific gain pattern and also integrate overall direction, which is the earlier formula that I mentioned earlier on. Okay, so the sky noise temperature, they actually can be varied with frequency. Okay, especially for frequency below 1 gigahertz, is because of this galactic noise here. So we need to take care of this. Come to a quick summary of this discussion on the antenna temperature. Okay, the antenna temperature is actually a key concept in understanding the amount of radiation an antenna receives, which can represent either the signal or also the noise. It actually depends on the application. Okay, it helps quantify the effective power of this radiation by linking it to the temperature concept, facilitate better analysis and system design in both, okay, both form of communications here. Okay, so with this, I'd like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for some support. I hope to see you guys soon. Bye for now. Thank you.